Okay guys, so welcome to intermediate analysis at the time of Corona crisis. I'm going to remind you of a definition of convergence sequences, and this is a definition of convergence sequences. So Pn converges if for every epsilon there exists a capital N such that if n is greater than capital N, then the distance from Pn to P is less than epsilon for some P in my metric space X, and that P is called the limit of Pn. We also use the notation Pn converges to P to indicate exactly the same thing. So there's a terrible burden with this definition, and the burden is that in order for me to conclude that the sequence converges, I have to know the limit of a sequence. Limit of a sequence explicitly is in the definition of the convergence series. So what I want to do now, and I did it last time, this is just a repeat of last time, I want to introduce another kind of sequences. These are called Cauchy sequences, and this is a definition of the Cauchy sequence. So a sequence Pn in a metric space X is called Cauchy. If for every epsilon greater than 0 and every n and m greater than capital N, so there exists an n such that for every n and m greater than capital N, distance from Pn to Pm is less than epsilon. Now, if you're a student, you may like this definition a little bit less than the definition of a limit, because it contains two different indices, m and n, and that kind of seems to be a little bit more burdensome. But the point is that this definition does not contain the limit. In other words, this definition contains only the terms of the sequence, which allows me to conclude, if I'm lucky, that the sequence is Cauchy without knowing the limit of the sequence. Now, the purpose of this lecture is, of course, that in many times being Cauchy implies that the sequence converges, and that's a great remedy, because you can conclude that the sequence converges without knowing what it converges to. And as an example that we will deal with later on, if you take a sequence Pn of numbers equals to 1 plus 1 over n to the power n, then the sequence converges, and in fact the limit of the sequence is known as E. But the point is that in order for me to prove that the sequence converges, I have to know what E is, and E is defined to be the limit of a sequence. I cannot prove that the sequence converges without knowing what the limit of a sequence is. Okay, so let's get back to Cauchy sequences, and the first result that I want to prove here is that this is a theorem. So the theorem says that if Pn converges, then the sequence is Cauchy. So this is the first good news. At least if the sequence is not Cauchy, then the sequence definitely does not converge. So let's prove it. And the proof is not very difficult. It does contain this cosmetic point about epsilon over 2, but I hope by now you are used to it. So suppose that Pn converges to P. That means that for every epsilon greater than 0, there exists a number n such that if n is greater than capital N, then the distance from Pn to P is less than epsilon over 2. I don't lose anything by choosing epsilon over 2, because it's just another epsilon. However, cosmetically, the proof will look a lot better if I choose epsilon over 2 instead of epsilon. Alright, so what happens if m is also greater than n? Well, then the distance from Pm to P is also less than epsilon over 2. Agree? And by triangle inequality, we conclude that the distance from Pn to Pm is less or equal than the distance from Pn to P plus the distance from P to Pm. This is less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. Alright, so at least one property of a Cauchy sequence is the same. At least one property of a Cauchy sequence is that it's a necessary condition for the sequence to converge. Let's deal with another property. And this property is, let me try to take a different page. So you should somewhere keep a note, I hope you do, of a definition of a Cauchy sequence. And so this is a theorem, next theorem. If the sequence Pn is Cauchy, then the sequence Pn is bounded. Now remember, we proved previously that every convergent sequence is bounded, and so at least if the sequence in Cauchy is Cauchy, it has that in common with convergent sequences. So let me do the proof here. The proof is very quick. So by definition of a Cauchy sequence, there exists an integer n such that if m and n are greater than n, this implies that the distance from Pn to Pm is less than, oh, I don't know, 7. So my epsilon in this case is 7. Okay? So in particular, the distance from Pm to Pn plus 1 is less than 7 for all m greater than n. Okay, so what have I done? I managed to find the ball around, or the neighborhood around the point Pn plus 1 such that, of radius 7, such that every element Pm belongs to this neighborhood if m is greater than n. What's left is only finitely many of those m's. So let me do that, and let's say r is equal to the maximum of the distance from Pm to Pn plus 1 for all m less or equal than n. Okay, so what does that mean? There are only finitely many of those Pm's, and so this distance is definitely a real number. Putting it all together, I want to say that the distance from Pn plus 1 to Pm is less than, say, 7 plus r. So if m is less than n plus 1, it's less than 7. It's less or equal than r, therefore it's less than 7 plus r. If m is greater or equal than n, then this distance is less than 7, and altogether it means that every sequence Pn or Pm belongs to the neighborhood of the point P sub n plus 1 of radius 7 plus r, and therefore the sequence is bounded. Okay, so far so good. What I want to do next is I want to prove a couple of theorems about the Cauchy sequences. So I want to prove that in particular, in some very, very specific cases, if the sequence is Cauchy, then the sequence converges. So you ready? Okay. This is the theorem 1 of this kind. If X is a compact metric space, and Pn is Cauchy, then Pn converges. So a few words about this particular theorem. This particular theorem says that in a compact metric space it's enough to know that the sequence is Cauchy to conclude that the sequence converges. A few more words about the proof of this theorem. The proof given to you in a book is absolutely beautiful, it's gorgeous, it's elegant. It is a little bit less intuitive. So I'm going to give you a worse proof. I'm going to give you another proof. Of course, in a test, you're welcome to do either proofs, but the proof that I'm going to give you is kind of more towards what we're proving and less tricky. You should read both proofs and understand that my proof is essentially the same as the proof in Rudin, except he uses his tricks to make it all very, very beautiful. Ready? Okay. So let Pn be a Cauchy sequence and let's suppose that Pn is the range of the sequence. Well, what does it mean? It means that Pn is a subset of a metric space X, which is the range of this sequence. Okay, now I know that the set Pn is a bounded set, and so if I take the closure of this set, this is also a bounded set. And this is why basically we have to study most of the things that were studied in a previous chapter about topology in order to make this couple of theorems work. So I know that this Pn is a bounded set. I know that the closure of Pn is a closed bounded subset of a compact set, and therefore I know that Pn has a limit point. So let P be a limit point. Now remember that this means that there exists a subsequence Pnk of the sequence Pn such that Pnk converges to P, to that limit point. Okay, so at least I found out that there exists a subsequence of my sequence that converges to this particular limit point P. What's more important is I got a hold of some particular P that I can deal with now without worry about it. So once I got a hold of it, I claim that the whole sequence converges to P. That the whole sequence Pm converges to this very same P, which is the limit point. Okay. So why would that be? The fact that Pnk converges to P means that there exists an n such that if n sub k is greater than n, this implies that the distance from P and K to P is less than epsilon. Agree? This is what it means for the subsequence to converge. Okay, now on the other hand, there exists another n, say n1, such that if m and n are greater than n1, this implies that the distance from Pm to Pn is less than epsilon. Again, let me change it to epsilon over 2 just to make it a little bit prettier. Any problems so far? I hope not. So let's suppose that n2 is, as usual, the maximum of these two numbers, and n1. Yeah, so I'm going to change this to epsilon over 2. Okay, then what happens? Notice that Pm n sub n is greater than n2 implies that the distance from p n sub m to p is less than epsilon over 2. If m is greater than n2, this implies that the distance from pm to pn sub m is less than epsilon over 2 because the sequence converges. Remember that this condition holds for all possible n and m. In particular, it holds in a case when n is really equal to n sub k. Now, the conclusion now, again, by the triangle inequality for the nth time, is that the distance from pm to p is less or equal than the distance from pm to pn sub k plus the distance from pn sub k to p. Now, the second distance is less than epsilon over 2. We know that by our assumption the first distance is also less than epsilon over 2, so altogether we get epsilon over 2 plus epsilon over 2, which is equal to epsilon. And if you read what I wrote that there exists for every m greater than this number n2, distance from pm to p is less than epsilon, and this is exactly what it means, that the sequence converges. Great theorem, right? So now if you're in a compact metric space, then you're definitely safe, because now you know that the sequence, every Cauchy sequence converges, and you don't have to guess the limit of the sequence to conclude that the sequence converge. Here is another application of this theorem, which is most important for us, and this is an application when we're dealing with those spaces Rn. Remember, most of this course is about the spaces Rn, or just R. And so this is the next theorem. And the next theorem says, again, that if Pn is Cauchy in the metric space X equal to Rk, and this is Rk with the usual metric being given by the norm, then Pn converges. Well, and here is a proof. And the proof again uses the previous theorem. So we know that if Pn is Cauchy, Pn is bounded. So the set of those terms is bounded. So the closure of this set is a closed and bounded subset of Rk. And again, at the very, very last theorem of the previous chapter, we proved that a closed and bounded subset of Rk is necessarily compact, right? So now if I take my X to be this space, then I know that X is compact. And I know that a sequence Pn is a Cauchy sequence in X. And since I know that this sequence is a Cauchy sequence in X, I know that the sequence Pn converges to some element P in X, and that means that the sequence converges in Rk. Notice that the definition of convergent sequence, if it works in a smaller metric space, then it works in a bigger metric space, and this is a big result. And as I said before, this is pretty much the main reason why we had to study all those topology in chapter 2 in order to make that conclusion, that in order for us to know that the sequence converges in Rk, all we have to do is make sure that this sequence is Cauchy. We're good at it. All right. I hope we are. So, a few more remarks about convergent sequences. Or about Cauchy theorem. So, in general, let me go back to this previous page. In general, this is a definition. a metric space X is said to be complete so this is a definition of the word complete, and a metric space is said to be complete if every Cauchy sequence in X converges. So what we just proved here is that Rk is a complete space. We also proved that every compact metric space is a complete space, and as you will grow in the graduate school, you will see that there are many more interesting metric spaces which are complete, and this is a savior sent to us from above. Alright, so just another stupid remark: is every metric space a complete space? And the answer is not, because this definition of convergence depends on the metric space as well as the metric, and I'm going to give you, as usual, a very stupid simple example. Let me choose my X to be an open interval 0, 1, and let me choose Pn to be equal to 1 over n. Well, notice that Pn converges to 0 in R, and if it converges to 0 in R, that means that the sequence is Cauchy, but the sequence Pn does not converge to anything. Well, why not? Because if it converges, it should converge to 0, but 0 is not an element of X. And so, at least formally speaking, this Cauchy sequence does not converge in this particular metric space. Once again, I have to tell you that it's of course stupid example and artificial examples, but there are other important examples of metric spaces and a natural metric where Cauchy sequences do not converge. Unfortunately, at this particular moment, it's a little bit too early for me to introduce to you to those metric spaces, and so I will finish my discussion about Cauchy sequences at this particular moment. And before I leave this particular lecture, let me do a few more things. These are a few more results that will be very useful later on. So I think from now on, more or less, for the rest of the chapter, we will abandon metric spaces, and all our metric spaces X will be R. This was the only interest, and so all of our sequences Pn will be numerical sequences in R. And first I'm going to give you a few definitions. These definitions again looks a little bit unreasonable, but please remember them, because they turned out to be very useful in the particular cases. Okay, so definition 1. So let's suppose that the set of elements P in X is the set of all subsequential limits of a sequence Pn. So let's see what can happen. It is possible that the sequence is bounded, and then it has some very convergent subsequences that follows from the compactness of the closed and bounded set. It is also possible that this set is not bounded. So if this set is bounded, I'm going to define the Limbsoup. So this is the definition for this notation of Limbsoup of Pn. And if this set of all subsequential limits is bounded, then this is equal to the supremum of all p, where p comes from the set of all subsequential limits. Fortunately, it is the real numbers, and we know from chapter 1 that the supremum exists. Now, if the sequence is not bounded on the right, in other words, if some subsequence of a sequence p converges to infinity, so it's unbounded, in that case we will say that the Limbsoup of Pn is equal to infinity. So this is a definition of the notion of Limbsoup. It is not a difficult definition, it's no big deal, and let me give you a couple of stupid, trivial, elementary examples. So if I have, for instance, a sequence that consists of 1, 1/2, 1, 1/3, 1, 1/4, 1, 1/5, etc. So this is a sequence and it does not converge. There are two subsequences of this sequence that do converge. So the sequence of 1 converge to 1, and the sequence 1 over n converges to 0. So there are only two subsequential limits. There are only two possible limit points of this set, and therefore I'm going to choose the larger one of them, which is 1, and I'm going to say that the Limbsoup of this sequence Pn is equal to 1. Are we good? Okay, let's continue. Here is another example. I'm going to take a sequence, say 1, 1/2, 2, 1, 1/3, 3, 1, 1/4, 4, 1, 1/5, 5, etc. 1, 1 over n, n. So what about this sequence? Well, first of all, the sequence is unbounded. The subsequence of this sequence consisting of 1, 2, 3, 4, etc. goes to infinity without any bound, and therefore I conclude that the Limbsoup of Pn is equal to infinity. Good? Okay. So the reason that this notion of Limbsoup is important for us is because very, very often we want to define something, and we want to define something as a limit, but we're afraid that the limit does not exist, and therefore we cannot define it. However, the Limbsoup is always existing, and therefore I can always define the Limbsoup. Are you okay on that? So a very, very, very quick corollary to this is if the sequence Pn converges to P, then the Limbsoup of Pn is equal to the limit of Pn and equals to P. Well, let's see. The sequence converges to P, so there exists only every subsequence of the sequence also converges to P, and therefore there exists only one subsequential limit of the sequence, and it's equal to P, and of course it's the largest one among itself, and so this is one of the reasons to introduce the notion of Limbsoup. In a very, very, very similar fashion, I can talk about Liminf. So once again, let me take a particular sequence, Pn, and remember right now I'm talking just about sequences in R and nothing else. And let's suppose that the set of P, of various P's, these P's are the limit point of the sequence Pn. In other words, there are subsequential limits. I'm going to take the least one of those subsequential limits, the infimum of those P, and I'm going to call it Liminf of Pn. Just as before, it is quite possible that some of the elements of the sequence Pn tend to negative infinity, in which case I will say that the Liminf of the sequence Pn is equal to negative infinity. Okay, so let me try one more example. before I leave you with that, and that is I'm going to take a sequence as before: 1, 1/2, 2, -2, 1, 1/3, 3, -3, 1, 1/4, 4, -4, etc. 1, 1/n, n, and -n, and they will go on like that. Okay, so what is the Limbsoup of the sequence? Notice that this numbers 1, 2, 3, etc. This is a subsequence of the sequence, and these numbers converge to infinity. So the Limbsoup of Pn is equal to infinity. Now on the other hand, I have the numbers -2, -3, -4, etc., and they go to -infinity. So my conclusion is that the lim_inf of Pn is equal to -infinity. Okay. To end this particular story about the Limbsoup and the lim_inf, let me observe a very important corollary that half of it we already did, and the corollary is that the sequence Pn converges if and only if the Limbsoup of Pn is equal to the lim_inf of Pn, and this Limbsoup and lim_inf is actually equal to the limit of Pn, and that's the sequence converges. Well, let's see. Suppose that the sequence is unbounded, then the sequence does not converge, its Limbsoup is equal to infinity. So that is out of the question. Suppose that the sequence is bounded, and the largest part of the subsequential limits is equal to the least one of the subsequential limits. That means that the whole sequence converges to the same subsequential limit, and the conclusion is that Pn converges to this limit P. Alright, so this is one thing. There is another note, another little useful theorem about numerical sequences, and I'm sure that you studied it somewhere in calculus 1 or 2 I guess, and this is a note about monotone sequence. So let's suppose that Cn is a sequence of numbers. This time I'm dealing strictly with numbers. It's a sequence in R. Now, among the sequences, there could be sequences that jumping up and down, such as, for instance, 1, 1/2, 1, 1/3. So some of the elements of the sequence will go up, some of them go down, and then go up and go down and go up and go down, etc. And what I want to do is I want to find a notion, a definition of a sequence for which this thing cannot happen. So I will say that the sequence Cn is increasing if Cn plus 1 is greater than Cn for all n. In other words, the next term of a sequence is always greater than the previous term of a sequence. I will say that the sequence is non-decreasing, and that's almost the same definition and not very important if Cn plus 1 is greater or equal than Cn. So it's kind of the same thing. So every increasing sequence is definitely non-decreasing, but there could be a non-decreasing sequence which is not increasing. Now I will say that the sequence Cn is decreasing if Cn plus 1 is less than Cn for all n, right? So the terms go down, and I will say that the sequence is non-increasing if Cn plus 1 is less or equal than Cn. So notice that the sequence is increasing means this inequality has to be true for all n, not just for some, but for all. and the sequence is decreasing if this inequality is once again true for all n, not just for 1. And the sequence Cn is called monotone if it is either non-decreasing or non-increasing. Cool. Okay. So for instance, if I take the sequence 1/2, 1 plus 1/2, 1/3, 1 plus 1/3, 1/4, 1 plus 1/4, etc. This sequence is not monotone, because judging from the first two terms, it definitely cannot be non-decreasing, and judging from the next two terms, it definitely cannot be non-increasing. However, if I look at the sequence 1/2, 1/3, etc., this sequence is monotone because it is non-increasing, and in fact it is decreasing because the next term of the sequence is always less or equal than the previous term. Notice that it has to be true simultaneously for all of those terms. On the other hand, the sequence 1 plus 1/2, 1 plus 2/3, 1 plus 3/4, etc. This sequence is also monotone, and it is increasing sequence. Now there is a little theorem which may look very, very little at the moment, but it is one of the most important theorem in applications to what I'm going to talk about next, because after this particular section we will start talking about the series, and this will be a completely different story. So at least for now, let me make a theorem, the theorem that you may know. This is the theorem that if I have a sequence Cn of real numbers which is monotone, then the sequence Cn is bounded if and only if, then the sequence Cn converges if and only if it is bounded. Okay. So in a particular, we know that every convergent sequence is bounded, so half of this theorem is already proved. What I want to prove that if in addition the sequence is monotone, then I can guarantee you that the sequence converges, and again I simplify my process by which I proved my convergence. I'm going to prove this thing for a particular case, the case when Cn is non-decreasing. Well, the other proof is exactly the same, and let's suppose that Cn is bounded. Well, if Cn is bounded, then there exists a number, let's call it alpha, which is equal to the supremum of Cn. Do you agree with me? Okay, so that means that for all n, Cn is less than alpha. Cool? Okay. So now I claim that for every epsilon greater than 0, Cn is less than alpha and greater than alpha minus epsilon. Well, why is that? Because if all Cn would be greater than alpha minus less than alpha minus epsilon, then alpha minus epsilon would be the upper bound and not alpha. So the conclusion is that Cn minus alpha is less than epsilon, and therefore the sequence Cn converges. Okay. So this is what I have for the first installment of Tuesday lecture. I'm going to pause for a minute, and then I'm going to record the second installment of that lecture. And please read the book. The same theorems are presented in a book, and they're very, very important for this particular chapter. Thanks.